All right, so this one is interesting. The area, no, it's not a trough. The area of the triangle that is cut off by the first quadrant, whose hypotenuse is tangent to. Ooh, I love it. Ooh, that's so evil. Sorry. All right. So they want the triangle cut off by the first quadrant, whose hypotenuse is tangent. So basically, it's going to look like, this triangle here, cut off by the first quadrant. So its hypotenuse is going to be flexible, right? But they want the hypotenuse to be. So let me. If I knew the equation for this, then I could figure out the area of the triangle. I don't know if you guys are with me, because then I can figure out the intercepts, for example, right? And then I can get the area of the triangle. Are you with me? Yes. So when I read this, even before I know how the hell to do anything about the problem, I say they're asking me to minimize the area of a triangle. Okay, so I got to find the formula for the area of the triangle they describe. So now I have a goal in mind. So they say find the biggest blank, whatever they say after that. I got to get a formula for this, so I can attack it with derivatives and get the minimum and maximum of it. That is how you go through this. Now, it doesn't fill in the blanks about how the hell do I get the area of the triangle, but at least gives you a goal, right? Now, this one says, where'd it go? Oh, there. The hypotenuse is tangent to the parabola y equals 4 minus x squared. So here's my parabola. So it's got to be tangent. So you can imagine my hypotenuse could be this guy, or it could be this guy. See, so it's tangent at some point on this parabola. And the formula for the parabola is 4 minus x squared. So the hardest part about any of these problems, and I'm sure you guys have realized this, is figuring out what the hell how do you construct it. You want to graph what they're talking about and try to step back and see how does that relate to what I need. I need the area of a triangle. So I've got this side and this side. I'm just trying to get the hypotenuse. So if it was at this point, well, could it be this point right there? What's the derivative there? So any tangent line here would be flat. Would that make a triangle? No. It has the intersect here, right? So I can already eliminate that being a point, right? So it could be this point there, and then it would be the triangle that's tangent. So then it would be that triangle. Do you guys understand the idea behind how they're creating a triangle out of this? It's cut off by the first quadrant, so the legs are these. I just don't know where the hypotenuse is going to be. That's going to tell me how long these legs really are. All right, maybe. Let's stop there for a second. So how would I find the y-intercept? Maybe it's this point, so then it would be this triangle here. This really tall but skinny triangle. Because that would be the tangent line there. Well, I drew a horrible tangent line, but you guys get the idea. There it is. So it would be this triangle here, all the way up to here, and over there. Right? So that you can have a lot of different triangles in there. So ready with me on that part, how the space goes. So how would I find that? Why is that point important?
To know how long y is.
To know the height. Yeah, to know how long that y is. And of course, this point wouldn't tell you how big the base is. And then I just take half the height times the base. So when I read that problem, it's been forever since I've done that problem. I can't even remember doing that problem. But the steps I took to figure out where to go is, number one was just, what the hell are they talking about? I want to minimize the area of a... Okay. So I want to get a triangle somehow. How am I constructing this triangle? It's cut off by the first quadrant and the hypotenuse. Oh shit, alright. Hypotenuse controlled by this parabola. Oh shit. So I try to bring all this stuff into this. Controlled by, so if it's up here, it's going to be really fat. If it's down here, it's going to be really tall. So now you're like, well, okay. One more step. How do I get the equation of this? Because if I get the equation of this, I can get my y-intercept, my x-intercept. What steps would I take to get the equation of this tangent line? What do I need first to get the equation on the tangent line? Slope. That's crazy. Right. I like it. So what point does it go through? X comma 4 minus x squared. I like it. So what's the derivative? Negative 2x. I like it. So the slope at any point x is going to be negative 2x. Is that cool? Let's call our point, well, doesn't really matter, but let's call our point x1 so that it's 4 minus x1 squared. Just to make x1 as a specific value. I just don't know which one yet. So the idea behind this is I can make a lot of different triangles if I just pick a different tangent line along this parabola. There could be a lot of different shaped triangles. I want the triangle with the smallest area. So there's some point on this parabola whose tangent line, if it's used as a hypotenuse, will make a small area triangle, the smallest area triangle. That is the whole idea. Right? So what's the slope at x1? It'll be negative 2x1. So then what's the equation of the tangent line then?
The slope-intercept form? Or the slope point form?
Sure, yeah. So my point is this. Oh shit. So then my equation of my tangent line is going to be y minus y1 equals m x minus x1. And of course x1 really is x1. Now find the y-intercept, that would be the height. Find the x-intercept, that would be the width. Be really careful. x1 is a number, bless you. So if you wanted to, you could use a different letter than x1. You could use a, b, whatever, right? If that makes it better. And maybe that would make it better. I'm just choosing a value for x. So this point would be a, comma, 4 minus a squared. Is that cool? If it's sitting on the parabola, that's what the point's going to look like. So maybe without all these freaking x's thrown around in here, it might be easier to look at. So now when I say find the y-intercept, how do you find the y-intercept always? Set x equal to 0, right? And then how do you find and that's going to control your height. So now you're filling in your area formula at 1/2 base times height. So figure out the height by finding the y-intercept. Figure out the width, the base, by finding the x-intercept. And then you got your equation that you're going to take derivatives of and so forth. Oh, I went further than I wanted to, but I got excited. This is a cool problem. I mean, it's. I almost feel certain that none of you would describe it that way, but it's just you can sink your teeth into this problem, and this is unsatisfactory, right? Because there's no numbers in it. How is this an equation of a line? Well, it is because I followed the procedure. I just don't know what point I want to use. So of course my slope is dependent on a and so forth, right? So this is every equation of every tangent line to this parabola. That's what that is. So of course it's going to look a little ugly because it's representing an infinite number of lines at once. It's a little difficult to do. Okay, that's, if you're not sure where to go from there, that's actually, most of the work is almost done there. Is that okay, John? Is that what you were trying? Anything else from homework? Yes? 39? The one about the Pac-Man? Okay. That one, let's see. Alright, so everybody got what they want from this here? Okay. This one's kind of neat because you're constructing like a drinking cup by taking a circular piece of paper and then cutting a little quadrant out of it, a little, not quadrant, but a little sector out of it. All right, so you are making your dying Pac-Man. Radius R, big ass R, and they're just calling this A, B, and C, like that, just to put stuff in there. So it spells crab. I don't know if it, sort of. So they join CA and CB. So it kind of makes sense. If you try to join these sides, it's going to push this out. Can you kind of imagine that? That's how you can construct a. Yeah, exactly. You can construct a conical cup. Try to say that all. That. Find the maximum capacity of such a cup. And capacity in this sense means volume. So you're trying to maximize the volume. So the hard part about this equation, about this problem, is how the hell are you going to construct the volume formula for this cup? You've got to think ahead about what's going to happen when you try to join these. So when I join them, this is going to push out. The problem is, how much is it going to push out?
Radius will become height, right?
Not quite.
Not quite.
Well, if I do this, it'll be kind of slant height. Do you see? You know? So if I do join them, I'm going to get this cone. This one reason they made it a big ass R. Just let it go, Jim. Is that the radius of the circle I've created? Is that R the radius of the circle?
Yeah.
Where is the R on the cone? Yes. Okay, that'll work. So this slant height. That's actually an official name of it. Slant height. It's the height that's not perpendicular to the ground.
So draw a triangle over there.
That might become handy, right? If you draw a triangle involving the height and that radius, because the volume of a cone, of course, is what formula?
1/3.
1/3
area of the circle.
Area of the circle
And height.
times the actual height. I like it. So here's the actual height. Here's the radius of the circle. So this is the function, this is the formula you know you're going to work with. This is awesome. I don't have to construct it myself. I just have to fill it in. The not so awesome part is, how the hell do I fill this stuff in? Big ass R. Big ass R. Is it a variable or what is it? Constant. I love it, because we're given a circle of radius R that I'm cutting something out of, right?
Oh.
That's given to me.
Good.
Are you guys, so it's a constant. Why is that important? Because once we start taking derivatives, we've got to know what the hell a constant is versus a variable. It's going to change my derivative, right? So I don't have to worry about big ass R. Wherever it shows up, it can stay there. It's just a constant. It's my variables I got to do something about. And basically, we're just giving it all away. Just about, again, I get excited. Do you have too many variables in this? Of course you do. So that kind of gave it away. So that's as much as I'm going to say. If you're like, what? You didn't say anything? I said too much, to be honest. So you're almost done with that problem too. Believe it or not. Like, I choose to not believe it. Okay, then come see me. We've done this kind of thing so many times. You have two variables. You need a relationship between them, so you can get rid of one of them. Bam. This is the kind of thing we've seen a lot. Alright, I like when I look at some of the... Sure. You gotta try it out. Cool. Yes. 70? John, you just want everything. Oh, now this one... Alright, let me see if I can tell you something without doing much. This is kind of neat because I don't have too much pride to admit that when I was younger, I lived in the attic of this cool house on the East Coast, and I know. And I got a new bed. I had this old bed that I had forever, and I'm like, it's time for a new bed. So I got this new bed. I'm like, yeah. So I took the mattress up there, yeah, and then the box spring. Shit, it won't. Oh shit. The math teacher forgot to do the math. It wouldn't turn the corner. So this is sort of. So I had to leave it on the second floor, and we had to move it this way to go out the front door, and I had to move it this way to go up into my room for a while. But anyway, memories. This problem is basically sort of like that. You got this pipe. You're seeing how long can the pipe be to actually make this turn. They give you everything you need. How can I say this? How do you get the length of that pipe? I mean, let me see if I can do this without saying too much. So here's the pipe that got in this position. Here's theta. They tell you that this is 9 and this is 6. So all I'm going to say is, do you see two triangles up there? And you're trying to maximize what's the length of the longest pipe. You're trying to maximize the length. You're trying to get a formula then for the length. Do you see? I mean, sometimes students have trouble with that. And if you have trouble with that, you ain't going nowhere. Maximize the blank. I need a formula for the blank. So then I can attack it with derivatives. So then at least you know what to try to do. Now, I'm not saying that that's the hardest part, but without that part, you're screwed. You can't even try to do anything. So I need to get a length for this. Aren't there two triangles up there related to those lengths? Okay, that's all I'm saying. That's it. That's all I'm saying. There are two triangles that relate to the length. If you can write a formula for the length, you can attack it with derivatives. Attack it with derivatives.
Okay.
Cool. I like it. Okay. Anything else from homework stuff? All right. I told you to come ready with your questions from 4.7 because I'm not going to talk anymore about 4.7. We're going to get into 4.8. It's crazy how that works. This is we're going to look at a procedure, an algorithm that calculators use a modified version of this algorithm to figure out roots of equations. And the idea behind it is so simple but cool, and I desperately wanted to show you guys an example here, but it won't let me. Let me try one more time. This is weird. You know you're desperate when you try to use Internet Explorer.
American Online.
Ask Jeeves. Let's see. No? Nobody remembers Ask Jeeves? Yeah, it still won't let me. Whatever. Whatever, you stupid thing. Alright. Wait, this might work. It's slow. Come on, come on. Okay. Come on, dude. No, you suck. Let's try you. One of these browsers has to work. You think? Alright, I'm going to let it think. It's going to come back to it because I'm going to try to draw on this, but that always is exciting. So let's say I had a function that had some intercepts, and I want to try to figure out what that intercept is. I'm not sure what it is, and I don't have a graph to work with, right? So this is a computational way to find the roots. So we are trying to explore, students often say, well, my calculator does that, why don't I just use that? Well, then the whole part of math is, what math does the calculator use to figure it out? It's not just magic calculator dust, right? Now the calculator's ready. Yay. No, it's got to use math to figure this shit out. So we're the humans that invented math. We have to be able to use the math. Oh, cool. Okay. Sorry. I feel so much better for you guys. All right. I think it was... Who won this time? Which one are you? Internet Explorer? No. No. No, it was Internet Explorer. That's funny. Oh, well. I think Bill Gates just got excited for, he's not sure why. Oh, Safari? No, there's no Mac up here. Alright, so, thank God. Because it's much easier to understand if you can see a decent visual representation of what's going on.
Your pictures are not that bad.
Considering that I can do this, they're pretty bad. All right. So here's the idea. So this guy's got two roots here, right? This is a slice of cosine. That's what we're using there. Slice the cosine. Can you guys all see that part? All right. I just needed Kevin to say this. That's all I was looking for. So the idea is I can use a guess. And this is such a cool way to use derivatives. Let's say that little black dot is my first guess. And that's a decent guess, especially if pretending that we don't have this graph, we can't get this graph. So I am going to talk about how do you get a better guess to start with. Because if your guess is bad, this algorithm just go crazy. Just go to infinity and like, I don't know shit. So your guess has to be decent. So we will talk a little bit about how to make a good first guess. But let's say that's my first guess. How are we doing so far? Now here's the nifty idea behind this. If I look at the output for this and then make the tangent line, what happens when I do that? Let's see. Bang. You kind of with me? So the tangent line to the point that my guess makes on this graph is this. That would be my second guess. Then I do it again. I make another tangent line. Stay with me now. I make another tangent. I drop that. That's my next guess now. I make a tangent line from it. What's happening? Dude! So that's kind of awesome. And it sort of makes some sense. Now, of course, there are spots on the graph that will never work for you. For example, if my first guess was somewhere in here. Oh, how do I move you there? Why is that a remarkably bad first guess?
Because it's past the trough. It's the minimum.
I'm trying to get like right on the middle. The tangent line is going to be almost horizontal. So then where's it going to intersect the x-axis? Well, if it's almost horizontal, it could intersect the x-axis at like, x of 90,000 something, right? Or negative, right? So if I try to do this, it's going to try to do something. Let's see what it does. Now, if I make it a little less bad, let's see if it's able to come back in. No, it never recovers. So what I'm doing is I push. This is my first guess. It makes a second guess. It makes a third guess, and it's just off the screen. Are you guys kind of understand? So my first guess is either far away. Now, that's almost as close as my first guess was over here, isn't it?
Yeah.
If I make my first guess, well, I got to be careful because coach Jeff. Come on. I can't. Well, I don't want to get too close to this guy, right? Because the same problem's going to happen. Let's see if this is something it can handle. Yeah. It actually finds that other root, right? So that's the other thing that might happen. Especially when you have a function that kind of curves back on itself. The tangent line you draw might take you to a different route than the one you wanted. Okay, maybe. So there are pitfalls to this, and that's why the one the calculator uses is an adjusted form. So when the calculator does its first iteration of this, and it says, I'm getting 80 billion, which is a little bit bigger than their guess. It modifies itself to make the first guess better. So they do have a different kind of algorithm. But this is the basic platform that it's built on, is the idea. This is called Newton's method, right? Because a guy named Newton kind of made it up, right? And said, oh, look at that. It does stuff. So if I get my guess closer to this root, it'll find it. This is kind of cool to leave it just on. See how it finds it pretty quickly? And now if I get over here, look, watch. The tangent line takes it way out. Come on. And then I get close to that. And then if I get closer to that root, it's going to find that root. Now it might take, let me see if I can put it somewhere. Here we go. It might take several iterations. Get in there. No. All right, that's fine. So the third iteration is pretty much there. And look, here's what I'm getting for my guess. And you can see here, see how it stops changing to the 9 there? So that's going to be a really good guess there would be 4.71239. Are you guys semi with me?
Yeah.
Okay. All right. So it's not too freaky. It's not too bad. So here's how it's going to work on in real life. Now, obviously, there's a lot of math behind this because I go ahead.
How did you get when you took your guess and then you drew it to the?
That's what we're about to get into.
Yeah.
Your tangent line is going to require some math.
Okay.
Sort of like the one we just did, the last question I had. You have to build the tangent line off this first guess. Thankfully, it's not going to be. It's going to be an actual number, so it'll be a little easier to work with. So here comes the math, right? So that's the idea. The idea is really pretty simple, but to construct the tangent line is going to take a little work.
One more.
Yeah.
How do we not, like, the guess it seems pretty precise. Like, you got to be between like 1 and like 2.5. It's pretty. If you get
Well, it depends on the function. It depends on how quickly the function is up and down, and that happened before. You know, if the function is really going crazy, then I've just got to be even more and more and more precise.
So how do, like, I get it's a guess, but it's like, it's got to be a pretty accurate guess.
Yes. So
How do you make your guess so accurate?
let me show you this. So if my function was, and this is related to a handout I'm going to give out, just because I'm thinking about this. If my function was this.
Are we going to guess its roots?
Say again?
Are we going to guess its roots?
But not just blindly.
Yeah.
So here's where pre-calc is supposed to have helped you out. You should be able to draw a rough sketch, semi-rough sketch of natural log, for example. What's natural log's root?
Yeah.
Oh, shit.
-1.
No.
Negative.
Where's natural log's asymptote? Vertical asymptote? 0. It can't go below 0. It can't even be 0. But where does it hit the x-axis? 1. Natural log of 1 is 0. So here's a rough sketch. And natural log of e would be 1, right? So e is about what?
3, 4.
Sure. So he's a little bit below 3. So about there it's going to be 1. Are you guys kind of with me? I mean, this is the level of sketch I'm talking about. It's not perfect, but it is a little more precise than going, yeah, like that. Right? It's a little more precise. So here's what natural log looks like. And what I'm really doing is this. I want to let this equal 0, right? Which means I want natural log to equal sign. That I can kind of show visually to myself what's going on. So there's natural log. How does sign look?
Wait.
Starts at 0.
No way. Yeah, good. Starts at 0. It hits 1 when? Pi over 2, which is roughly
Half of 3.1.
1.6.
2. So like 1 and 0.57. Yeah. So 1.57, it's at 1. Right? And then it hits 0 again at pi.
3.
So here's what sine looks like. So what's a good first guess then?
Okay. 2.
Like about 2. Do you guys understand what's happening here? This is the step that you take if you're doing this kind of problem honestly, which means you didn't just immediately graph it. That's kind of against the idea here. I want to see what the graphic calculator does to do this. I can't use the graphic calculator then to do it. I'm like, I see that button. No, screw that shit. I want to see the math behind what it's doing. So that would give me the first guess for this. And then I would run off to the races and do this kind of thing. You guys semi with me? So it's a really good question because your first guess has got to be decent. Doesn't have to be perfect, but the weirder your function is, the better it's got to be. Or who knows where it could send you off to, right? Okay, in fact, you guys remember when you try to find a root in your calculator, it doesn't ask you for a left bound and a right bound? Do you understand now why it does that? Because if it does and it gets out of there, it's like, no, let me adjust the guess. Whatever guess you gave it, it's going to adjust it somehow and see if it stays within those bounds. So that's a little extra thing that it adds in. All right, so what does the math look like behind this? I don't know. Let's see. So what I want to do is I'm given a function. I want to find the roots using derivatives. So what I really want to do then to bring the process down is I want to take a guess at the root. Let's say our first guess is x1. It's amazing. Now I need to construct the tangent line and then get the x-intercept for the tangent line. That's going to be x2 then, isn't it? Is that true? Yes, it is. Yes. Okay, good. So just like we saw there, my first guess is here. It builds my second guess. That builds my third guess. That builds my fourth guess, so forth. So it's going to be, I'm going to keep doing the same thing over and over. And every time I hit enter, it's going to refine my guess. Refine. Hopefully, as long as my first guess was decent enough. Maybe. So, how do I get... So what do I know here? I know, what's the... to construct the tangent line at x1. And let me say this better. At x1 comma what?
Yeah.
F of x1. That's right. So I got a point. What else do I need?
You need the equation.
To get the equation, what else do I need? I need to get the equation of the tangent line. I need a point that it goes through
Slope.
and the slope. I love it. Yes, semi with me. So where's this on the picture? Here's my first guess. That is the point I'm talking about right now, right? That's x1 comma f of x1. That's the point. It's what I created the tangent line through. Okay. All right. So as I just get to the point now. All right, we're getting there. Of course, what else do I need? I'm sorry, I think you just said slope. So how do I get the slope? No way. So then the slope at x1 would be what?
X1.
All right. Too nice to believe. It doesn't have to do any work. You just have to say prime that bad boy, right? All right. Now, here's where you got to realize. So that's my m. This is my x1, y1. So what's the equation of the tangent line look like? Y minus
Minus f of x1.
f of x1 equals,
M.
And
which is f prime.
X minus X1.
I like it. Cool. So now find the x-intercept. Do it. That's the equation. The easy part now should be finding the x-intercept. So I left you the easy part. Just algebraic manipulation, that's all.